This is a tough question. One, because it's not an obvious starting point. And secondly, it's very easy to go down the wrong path once you've made a starting point, get like complicated algebra or go to a dead end or something. So when I did it, I noticed these two similar triangles in blue and these three in red. And I started trying to write equations down. So I had to, I didn't know what this length was, so I had to say call this x, and then this one here was L minus x, where this length was L, and similar over here, I might say this is y, and then this is L minus y, and I was writing down a system of equations using similar triangles with all of these things in, trying to just get down to an equation with L. I think I did so, but it was just like so complicated. It involved lots of square roots and it just seemed like it wasn't going to work. So I abandoned it. I've actually not got my working on that now. And it wouldn't be a good method to tell you about anyway. Instead, I'm going to go through two methods of doing this question. The work solutions describe three of these, but the third one involves addition formulae for tan. And like, first of all, that's like a year 13 topic. And secondly, it just seems unnecessarily complicated when these other two methods work pretty well. So let's go for it. The first way, which does include similar triangles, but it actually uses this subtle diagonal here. This is the diagonal of the square. And why does that create a pair of similar triangles? Well, if we say that this angle here is x, then because that blue line is a diagonal, then this angle is 45. Which means this angle here is going to be 45 minus x. But then I know that this triangle here is a right-angled isosceles triangle, so the other two angles in it must be 45 degrees, which means this here is also x, because then these two will add up to 45. And there we go. There are our similar triangles. Let me just highlight them in color. So I've got this blue one. Actually, technically, I haven't really explained why they're similar yet. But it's because they both have a right angle and this angle of x in, and that means the third angle, it must be the same for both, for this one and this one, and that's what means they're similar. So I'm just going to add some lengths onto my diagram. I've got 5 here because the area of the smaller square is 25, so I can square root to get 5, and then I'm going to say that the bigger square has length L. So this up here will also be 5. Now I'm going to draw out this purple triangle. And then I'm going to draw out the blue one just underneath in the same orientation. So it's a little bit smaller. I've rotated it round. So this would be U, which I've rotated it and reflected it. We've got B and S. That might help. And then here I've just got Q, P, and U. Well, we've got 5 here and then L plus 5 here. I'll add that on. The blue triangle, this is a result I'm going to use a few times now, and I've actually already mentioned it a few times in this Senior Maths Challenge, but I'm just going to imagine you haven't watched any of the videos. Fair enough. Then when you get a right-angled isosceles triangle here with L and L, you actually get root 2L as the hypotenuse because it's L squared plus L squared, which is 2L squared, and then you square root it. So I know straight away that the hypotenuse of the blue triangle is going to be root 2L because here's my triangle I'm referring to, which is L by L. So the hypotenuse of it is root 2L, which becomes the hypotenuse of that blue triangle. I don't know what SV is, that's quite awkward, but I do know that VU is, well, it's the same length as VQ, but actually remember again, it's in a right-angled isosceles triangle. So it's going to be um, the purple hypotenuse is going to be root 2 times that blue length for the same reason as I explained down here. So if I can work out the purple hypotenuse, which I can because I have two sides, I can then divide through by root 2 to get that blue side there. So I'm going to get L plus 5 squared plus 5 squared square rooted, which gives me L squared plus 10L when I multiply out those double brackets, plus 25 plus 25, so plus 50, and then square rooted. That's going to be this length here. And hence that becomes actually this side here. It's the same thing, but I'm dividing by the square root of 2. And then I've got two similar triangles, and I can use like scale factors to link them together. I can say that the square root of L squared plus 10L plus 50 divided by root 2L, that's the bigger hypotenuse divided by the smaller hypotenuse to get the scale factor going this way, will equal L plus 5 divided by root L squared plus 10L plus 50 over root 2. I'm not just going to directly start cancelling. I think it's going to be easiest if I cross multiply. So that will give me root L squared plus 10L plus 50 times root L squared plus 10L plus 50. So I'm basically squaring it, and then I'm dividing through by root 2. And that is then going to equal root 2L times L plus 5. This is really good because now I've got L squared plus 10L plus 50. After I've squared the square roots, I'm going to times through back by that root 2. I'm going to get 2 lots of L squared plus 5L, which is then 2L squared plus 10L. Great, these two actually cancel, and suddenly it all comes together. L squared equals 50. That is the area of the square, and that is our answer. So that diagonal made it all come together, whereas trying to look at other similar triangles actually doesn't, which is, yeah, again, what makes this a particularly difficult problem. Here's a second, completely different approach. We have to, oh, this sounds a bit of a pun, we have to think outside the box, and we're actually going to create a box around it here. So again, subtle. I mean, any method for solving this problem, I think, is going to be pretty subtle. So in the word solutions, they actually use A and B. I'm going to stick with L and phi, but they do manage to prove a really nice general result that actually, whenever you have this set up, this ends up being twice the area of this, which you might want to go and try and prove yourself after I go through this solution. But it's pretty cool, I think. But I'm just going to stick with L and 5, and that will also be 5. And then this here will be L. So I'm now going to say that introduce this being x. I don't know what it is, just going to call it x. That means that the total height is going to be x plus L. And then I can work out what it will be on the green side. So if this total height is x plus L, then I must get x plus L minus 5 here. Now, for the particularly subtle bit of the question, we have to realize that these two triangles are actually congruent. So they both got a right angle, and they both share a side. That's a good start. And then this angle here and this angle here must be the same because this one, so these two must add up to 90, and these two must add up to 90. And that's, there we go, that's why they must be the same. And then this one will be in purple as well. So I can now use that because I therefore know that this length is also going to be x plus L minus 5 because it's the same as this length. And then I also know, remember, that, yeah, the height is x plus L, so this must be x plus L here to here. And I can write down an equation because I can now equate the top length, which is going to be 2x plus 2L minus 5, to the bottom length, which is just L plus 5. The L's partially cancel, and I can get x. I can write down 2x is going to be 10 minus L, so therefore x is equal to 10 minus L over 2. So I managed to get all the lengths in this scenario in terms of L. Let's sub them back in. So x plus L will suddenly become 10 minus L plus 2L over 2, because L is just 2L over 2. And that will get me L plus 10 over 2. Let's change that now to L plus 10 over 2. And I could do the same with x plus L minus 5. Um, so that is going to be very similar, but I'm also minusing 10 over 2. Actually, this is going to become L over 2. I've used congruency. I've just got to now use similar triangles. I didn't bring this in before, but I've also got this blue triangle, which is going to be similar to the triangle above it, because you can see we've got a Z angle. So this purple angle will equal that one over there. I've got my right angle and I've got this shaded one. And then I've got 5 here, and the height is going to be L minus 5. So if I draw these two triangles out, the larger one, like which I'm just changing the orientation of, this is going to be L plus 10 over 2. And then I've got at the side, oh, I worked that out as L over 2, didn't I? So that's L over 2. And then in blue, we've got 5 and L minus 5. So then I can write down that L minus 5 divided by L over 2 is equal to 5 over L plus 10 over 2. And actually just times times through by a half, which actually would cancel out this. And then I'm going to cross multiply. Let me come down here. So I'm going to get L minus 5 times L plus 10 equal to 5L. So L squared plus 5L minus 50 is going to equal 5L. Cancel these two out. And again, we get L squared equals 50. I don't know, both approaches, obviously once you watch them, you're like, okay, I see where that comes from. Realizing them is another ball game. So first methods, go down the diagonals, make these two similar triangles and use them. And second method, construct a rectangle around the outside, fill in the lengths that you know, realize that these two are actually congruent, work out lengths, work out x, put it back in, then bring in this little similar triangle as well, and then everything works out. And like I said, if you change this to like m or something, you'll show that L squared is always equal to 2m squared. Really nice general result, worth looking into. The math is going to follow exactly the same as mine, so it's an opportunity to just practice it yourself. And then the third way, using tan and angles and stuff. Okay, have a look at the work solutions if you're interested in it. But good question, tough question. Well done.